In this synthesis problem, they're giving you a molecule to start with, and they're telling you what you want that molecule to turn into. And what you have to do is you have to figure out what you would need to mix that molecule with in order to make this transformation happen. Now, in the beginning molecule, you'll notice that you start with a pi bond, and that's a key sign. That means you're going to be choosing from some sort of addition reaction. That those pi electrons, those extra electrons in that pi bond, are really extra molecular glue that you can use to add something onto the molecule. So what did we add? Well, one thing that might stand out quite a bit is this OH. So we've definitely added an OH. It's not there in the reactants, and it is there in the products. Right? It's not there in the reactants, it is there in the products, so we've added that OH. The other thing we've added is a little harder to see because you have to see it with your mind rather than with your eye. And that is that in our original molecule, we had 2 hydrogens on that end carbon. But in our final molecule, we have 3 hydrogens on that end carbon. And so one of those hydrogens had to be added. So in this reaction, we've added an H and an OH. Now at this point, your mind should narrow down the possibilities to 3 reactions. Either it will be acid-catalyzed hydration, or it could be oxymercuration-demercuration, or it could be hydroboration oxidation. Those are the 3 ways to add H and OH onto a carbon chain. The differences between those 3 ways have to do with the notes that are provided for each of these reactions. So for example, acid-catalyzed hydration adds H and OH in a Markovnikov way. So does oxymercuration-demercuration. But hydroboration oxidation adds H and OH in an anti-Markovnikov way. So what did we do here? Was the H and the OH added in a Markovnikov way or in an anti-Markovnikov way? You can look at the 2 carbons in the double bond. You could see that the carbon on the left is bonded to 2 carbons, so it's secondary. The carbon on the right is only bonded to 1 carbon, so it's primary. And the hydrogen went to the right. The hydrogen went to the less substituted carbon. That is Markovnikov addition. So we know that this addition is going to be Markovnikov. Markovnikov, again, means that the hydrogen goes to the less substituted carbon. And it did. It went to the primary carbon, not the secondary one, in this reaction. Because it's Markovnikov, we know that this reaction is not going to be hydroboration oxidation. So now we're down to acid-catalyzed hydration, or oxymercuration-demercuration. Now the differences between those have to do with whether you can have carbocation rearrangement or not. In acid-catalyzed hydration, you do have rearrangement, or you can have rearrangement. In oxymercuration-demercuration, you don't have rearrangement. Now remember, in the mechanisms for these reactions, the first thing you do is you add the hydrogen. So the hydrogen forms. The hydrogen adds onto this carbon. And when it does, you form a carbocation, or you could form a carbocation at that other position. Now, if you form a carbocation there, will it rearrange? This is the big question. If it won't rearrange, or if we want it to rearrange, then we would do acid-catalyzed hydration. If we don't want it to rearrange, then we would do oxymercuration-demercuration. So first of all, could that carbocation rearrange? Well, it's not going to rearrange to the right. That would be a less stable position for the carbocation to be on. But to the left, this carbon is bonded to 1, 2, 3 other carbons, so it is tertiary. And if you formed a carbocation, it would rearrange to that tertiary position. And that means that the nucleophile would add to the tertiary position. But here we can see that the OH did not add to the tertiary position. It added to the secondary one. And that means that we do not want a carbocation rearrangement. Right? In the case of a rearrangement, that positive charge would move over here. But if it did, then the OH would attach there. The oxygen is the nucleophile, and it would attack that carbocation electrophile. Because it's not attached to this tertiary carbon, we want to prevent that rearrangement from happening. And the only way we can do that is by doing oxymercuration-demercuration. And so that would be the mechanism we need to use for this reaction. To make this reaction happen, you would have to add first mercuric acetate, so that's mercury with 2 acetate groups, and water, and that's occurring in a first separated step. And then in a second step, done separately, you add sodium borohydride. And so that is what you would have to add for full credit for this question on the test. You would not be able to add acid-catalyzed hydration. And if you just wrote the reagents for acid-catalyzed hydration without showing any work, you would get 0 points credit. Acid-catalyzed hydration, if you did acid-catalyzed hydration on the original molecule, you would end up with a racemic mixture of the 2 enantiomers with the OH on that carbon, because you would have had carbocation rearrangement. And since that's not what we want, we had to prevent rearrangement and do oxymercuration-demercuration.